will become low because the plastic if there is plastic deformation occurs, then it will increase the fracture toughness because that is another sink, and this is another mode of taking the energy. Okay, so if that mode is suppressed, when the plastic deformation is suppressed, then fracture toughness will less. That's why plane strain fracture toughness is always less than the plane stress condition. So in this when you do the test, okay, so the ASTM, American Society for Testing and Materials, so they give guidelines how to evaluate the fracture toughness K1C in plane strain mode. That means you have to use sufficient thickness. So when it will sufficient means how much thickness, so there are some guidelines. So that fracture toughness that you determine experimentally is small, because this value will be using as material property. If you use a thin specimen for the test, then you are getting higher value. So your design will be unconservative. Okay, to become conservative. So plane strain conditions are always ensured. Okay, in the experiment. So we will be talking about the plane strain fracture toughness in all our fracture mechanics lectures. So to summarize, the critical stress or fracture stress, this is the remotely applied stress. You are able to see the mouse in the PPT.
Yes, sir.
Okay. Okay, because I will be communicating through the mouse. The critical stress, that is remote stress for a component with central crack. Okay, so this is for a component infinite plate with the central crack. Okay, is product of root over of 2E gamma s by pi a. Okay, and E is young gamma is surface energy, and you know that when and A is the crack line. Okay, so this is ideal for brittle solids, which Griffith derived in 1921. And later, Irwin and Orowan in 1948, they corrected for metal because so Griffith did it for glass, which is brittle. But to extend it to metallic material, which have some plasticity. See, metallic material, even if you go, even if it is irradiated also, it doesn't lose its ductility fully. Okay, there will be some ductility is there. So no matter what you do, there will be some plastic deformation at the crack tip. So they modified their energy, surface energy, by gamma s plus gamma p, where gamma p substitute p stands for plastic deformation. So and in fact this gamma p is much more larger than gamma s. Okay, so for example in metal it is around 1000 times of gamma s. So you can tell that the critical stress for fracture will be twice root over of twice E into gamma p by pi a. Okay, and here you can see that as gamma p is greater than gamma s, so this the critical stress that is required for fracture, that is much higher. Okay, compared to the Griffith theory for brittle material. So this was Irwin Orowan's first modification. That means the surface energy they modified by including the plastic deformation part. Okay. Further, they modified this is the stress required for fracture, but generally we will not use in this form. What we will use? We will using sigma root pi a. Okay, that is using the stress. Okay. So that sigma root over pi a. So instead of A, they substitute by A effective, where A effective is the A plus radius of the plastic zone. Okay, and that radius of plastic zone estimation was given by Irwin and also later by other the scientists. Okay, we will be talking about that shortly. So let us now make it more elaborate. So this sigma fracture stress for any generalized material can be written as root over of twice E WF by pi a. So WF is nothing but total energy. Okay, including all the mechanisms of energy dissipation. For example, it includes plastic energy. It also includes elastic energy, the surface energy that already we have seen, that is very small. It also includes viscoelastic. Viscoelastic means, for example, when there is a viscous type of solid. Okay, that deforms with time, or viscoplastic. Okay, plastic deforms with the time. Those kind of effects. Okay, so it includes all the energy from all the things. Now, WF also can be influenced by crack meandering and branching. So you know what is meandering and branching? For example, in case of brittle materials or even from composite materials, crack will not go straight. Okay, so they will try to deviate from the path, depend upon it will take the weakest path. Okay, in the material. So here you can see that so this picture shows you atomistically how the crack overtake breaking the bond. In case of the metals, the crack will try to propagate straight by using plastic deformation. So you can see that as crack propagates, this zone, that hatch zone, you can see that plastic deformation occurs within the zone, and this is the shape of the plastic zone. So lot of energy is dissipated when crack is propagating. So crack is propagated by breaking bond. Okay, so that is source you are giving, but you are also giving additional additional energy for plastic deformation on the two sides, on the top and bottom. So total energy will be sum of this plastic energy and bond energy. Okay, that is what the urine and Oron correction did. And in addition to that, if the crack is branching, if now this crack is going zigzag manner, then what will happen? So when you are telling crack length, then which is the crack length? Because so the crack length will be nothing but the zigzag path. Okay, so here actual the crack length, if you see the projected area, that is small compared to the true area. That means the zigzag area. So that ratio of zigzag area projected area, that factor also you have to take. That means you have to give more energy because crack path is more. Okay, so here so if you are able to estimate all the energy that is going during crack propagation, either due to meandering or due to plastic deformation or due to viscoelastic or viscoplastic effect, so that the WF you should be able to estimate. You put it here, you will get the critical stressor factor. Okay. So as I told you, initially the G was 2 gamma S, which is energy released. Gamma S is nothing but the surface energy required for propagation of crack. That is only valid for brittle material, which is which Griffith did. And G is nothing but the K square by E. Okay, so if you see sigma square into A by pi A by E. So if you multiply, make it square, sigma square into pi A by E, will get 2 gamma S. And the sigma square pi A by E, okay, this is nothing but the energy released. That is energy that is given available for crack growth for unit area of the crack path. So the WF decides the resistance of material. For example, so WF here it is generalized form, that is work required for fracture. So this work is nothing but required for breaking the bond, making plastic deformation, making crack path crack to meander in the material, whatever it is. Okay. So this is also called resistance to crack propagation. For example, Griffith saw that for a brittle material like glass, once crack propagates, okay, then that energy that is required for the material, it remains constant. For that gamma is not more energy per unit area. Suppose crack that is suppose let us take thickness 1 mm, and then suppose for crack to propagate 1 mm, so you get 1 millimeter square per area, you require certain energy. Okay, let us say you require some 10 joules. Then further suppose crack to propagate 1 mm, you require another 10 joules. So per unit area, if you always say it remain always constant. Okay, that means the material resistance doesn't change with respect to crack propagation. So this is valid for brittle kind of material, perfectly brittle material. Okay, but you know when you go to the talk about metals, what will happen when the crack propagates? There is more and more plastic deformation is occurring. Okay, so instead of the constant crack resistance will increase. Okay, so that means for crack to initiate, you require certain energy, G critical, but for the crack to propagate, you require more and more energy. Okay, so that will call the resistance curve, and you must have studied that crack resistance curve. Okay, we will saw in the next of the slide. So for brittle materials, it is flat. Okay, that is some initial value, then it is flat with respect to crack line, it doesn't change. But when there is a moderately ductile material or having some ductility, then the resistance is not constant. The resistance will change. Of course, after some time it will become constant because it will the plastic deformation process will for unit area it will almost saturate. Okay, so this crack resistance concept, which was later derived, okay, that is taking into account the nature of the material which is resisting the crack. So let us slightly discuss it in detail. Now, for calculate the how to calculate the G. Okay, this so here is G means G critical. So you must understand two things. G is the strain energy, that is the potential energy release rate. That is, release rate means the critical value is a material property. Okay, that is determined for experimental value. Okay, but how much G you are giving to the material? How you are giving? By loading. Either you pull the material by giving displacement or giving load. So you are giving energy into material. So how to calculate the energy that is going into the material, and then once you know that, then you can compare what is material resistance. only if the applied value of G is exceeding the material distance, then only crack will initiate. Otherwise, crack will not initiate. Okay, that is the criteria, energy criteria. So, we will be discussing something how to calculate this G. Okay, you know that many times instead of G, the concept you use the case K1, that is G equal to K1 square by E, right? Young's formula. So, and then G equal to G critical means K1 square by E equal to K1 critical square by E. So E cancel. So K1 if it is greater than if it is less than K1 critical, then the crack will not propagate. If it is greater than K1 critical, K1C, the crack will propagate. That is the concept. So either you talk in terms of G or talk in terms of stress in the factor. Both are equivalent. Okay, for the linear estimate here. And you know that for different geometries, people have already given handbook solutions. Okay, how they have done by using FEM and other calculation methods. Okay, they calculated, for example, in case of a infinite plate with a center crack of length QA. So what is the stress and factor? K1C is nothing but sigma nominal, that is tension, into root over pi A. Okay, into the geometry factor which is approximately 1. Suppose the same thing, same geometry you apply some bending load. Okay, then geometry factor will be different. So this already in previous lecture must have taught you that different factors have been given, geometry factor. So you just refer the handbook. If you take the crack geometry what is given in handbook, if it is same as you require, then you take the formula K, that is stress in factor. You calculate how much, if you know this requires how much load. Suppose you know the load you are applying, how much crack geometry and dimension. Then you go to handbook, calculate the geometry factor, and then you calculate the nominal stress from your knowledge of load, and you calculate the K1, that is the applied stress in its factor. And then for this material, that your component made certain some material. For this material already experiment has been done. People have done experiment according to STM standard, and they have calculated the K1C critical value. Then you compare, just like you have the same concept. Your calculated K1 value, and this K1 value applied stress factor will be dependent upon the applied load. If load is more, K1 will be more. Okay, it is directly proportional to load. So if it is applied K1 value is less than critical value, then crack is safe. Otherwise, it is unsafe. So same thing, we can discuss this either in terms of G, that is energy release rate, or in terms of K. Both are same. And you know G for mode 1 crack is nothing but K1 square by E. So once you know G, you can calculate K1, or if you know K1, you can calculate G. Okay, so in this next slide, I will be discussing how to calculate the G. Then in general how to calculate G. Okay, that is strain energy release rate for a given geometry. So that G requires potential energy. So for potential energy we require two parts. One is the strain energy density, other is the work done by the forces. Okay, now suppose my load versus displacement curve is given by this line. So you know that work done, for example, there is a linear elastic bar of stiffness K, length L, area A, subject to the force F. So work done is nothing but half K square, so you know the half of force in displacement with the area under this curve. Okay, so if I increase more and more load, basically more and more work being done. Okay, and you know this work, external work, I also, so that is where it goes. It goes in storing of the strain energy. So strain energy density is calculated by half sigma x and epsilon x. This is called linear elastic material, which is nothing but integral of sigma x d epsilon x. Why I am writing this? This is already you people know in your BTech. So we will be using this concept to calculate the G, that is energy release rate. So the strain energy density in general, this is for 1D problem. Okay, this what I have seen is the 1D problem. Only that is one stress, one strain. If it in general 3-dimensional problem where we have sigma x, sigma y, sigma z, okay, and tau x, tau y, so strain energy density is given by the following expression you already know. So for this plane problem, so plane problem is both plane strain and plane stress I can combine. So the strain energy density, that is per unit volume, is given by 1 minus 4 nu, kappa plus 1 by 4, sigma square plus sigma square minus 2, sigma x y minus tau square. So plane problem is plane 2D problem. In case of plane stress, the third component tau sigma z will be 0, and for all these things tau xz and yz are 0. Okay, so we have only three component stress, sigma x, sigma y, and tau x y. Sigma z is 0 for plane stress problem, but for plane strain, when the thickness is large, so there sigma z is non-zero. And sigma z, you can always calculate this for sigma x and sigma y. And for this, so everything now